Welcome. We're going to continue on by talking about regression, so chapter 13 in your text. And as I alluded to before, regression is really building on correlation as a concept. The main thing is when we talked about a correlation before, we talked about an association between two variables. When we talk about regression, we're talking about this idea of prediction. So regression predicts, correlation is simply describing a relationship. I'd like to start out with simple linear regression, and this is really a statistical tool that lets us predict someone's score on a dependent variable based on their score on one single independent variable. And again, to reiterate, like we talked about in the correlation lecture, regression tends to work best with interval ratio or continuous variables. That's not to say that you can't put categorical, nominal, or ordinal variables in, but we're going to really try to keep this simple and just focus on interval ratio ones at this time. I'd like to use the same example that we talked about with correlation and kind of build on this to look at how we can turn this exact same research question into a regression example. So if you remember, kind of our big question was, is skipping class related to statistics exam grade? You can see here, if you recall, I had 10 students. I recorded their absences, their exam grade. I was able to take the mean and standard deviation, and ultimately where we went with this example was we computed z-scores for each variable, absences and exam grade. Once I had those z-scores, I cross-multiplied, I summed them up and took the average of them to create a correlation coefficient, or a little r. And as you recall, our correlation coefficient in this example was a negative 0.85. So your book in the correlation chapter, I believe it's on page 172, it also talks about something called the coefficient of determination. And this is really a tool that we can get from our correlation coefficient. And all we do to calculate the coefficient of determination is to take our correlation and square it. So if I take negative 0.85 and I square it, it'll get rid of the negative sign. And I would end up with a value of 0.7225, if you want to check that with a calculator. And really, this coefficient of determination is telling us this idea of explaining one variable using the other, or this idea of explained variance. So if you think of exam grade as a big kind of circular pie, what percentage of that pie am I able to explain or account for with absences? And in this case, it's simply the correlation coefficient squared. So I said before that ends up being 0.72. If I move that decimal to the right and turn that 0.72 into a percent, I'd be at 72%. So I could say that I think about 72% of my exam grade is made up by the number of absences I have. So really, regression is going to take this concept, our correlation, as well as our coefficient of determination, and we're really going to try to figure out what else can we do to help explain that variance in our dependent variable. So I know that's a little deep and heavy, but that's kind of where we're headed at a conceptual level. This might get a little bit messy right here, but stick with me. When we're talking about linear regression, we're really using the equation of a line to explain this. So this may take you back to some high school or college algebra. I have at the bottom here an equation of a line. You can see it's y with that little hat on it. Y hat equals bx plus a. I think when I took college algebra, we called it y equals mx plus b. So again, it's the equation of a line, a straight line. The actual symbols and notation you use doesn't matter a ton. And in this case, the intercept is represented by the letter a. And just again, an algebra refresher that the intercept is the predicted value of y when x equals 0. So it's where the line crosses that y vertical axis. And in this case, the letter B represents our slope. and our slope is the amount that y is predicted to increase for every unit increase of 1 in x. So in this case, x is whatever our variable is. Let's stick with this example and say it's absences. B is the slope, A is the intercept, and y hat is the predicted exam score we would expect. So here I have my scatter plot with absences and exam grade. So the dots look familiar. This is in the previous lecture as well. And I just went ahead and drew a line, and the idea is that this straight line is kind of the best fit for all the different dots on the plot. And I can get that line in a couple of different ways. Again, you see the equation of the line up there. We could calculate this by hand. So we could take the information we have, kind of those raw scores and our correlation coefficient, and we could calculate and fill in what goes in that line equation. And I should tell you that it's a little bit tedious to do, and again, not something you would probably do in your job or writing your dissertation. You wouldn't want to do that by hand. So instead, as an alternative, we can look at how we can run this in SPSS and generate the equation of a line from our SPSS output. I have a couple of shortcut commands here. I'm going to click over to SPSS, but really we're going to use this menu right here, and I'm going to show you where we can pull from the output to figure out how to generate our regression equation. And specifically, we're going to be looking for the slope and the intercept, or A and B. I went ahead and opened up SPSS. This should look somewhat familiar from last time. Again, I have my absence data, my grade data, and we're going to go ahead and run some regression commands to figure out how we can generate that regression equation, those coefficients. So if you recall, to run our correlation, we're under the Analyze menu and Correlate. I'm going to jump down one more menu to Regression, and you can see here there's lots of options to choose from. There's a lot that we just can't get into in this class, but for this class, we are always going to use linear regression, which is the second one down. So Analyze, Regression, Linear. Here we have the dialog box that pops up, and this is actually pretty user-friendly. It asks us for our dependent variable and our independent variable. So let's go ahead and put absences as our independent, and we'll put grade as our dependent. There's some different options and things we can click on, but for now we're just going to generate this regression equation, and we'll keep it pretty simple. So once I've transported those, I'm just going to hit OK. So if you remember with the correlation, it just gave us that little tiny box with our correlation coefficient. We have some more information here. This very first box is really just telling us what variables we entered into our equation. So you can see here we designated grade as our dependent, absences was entered as an independent. These next two boxes, model summary and ANOVA, I'd like to skip those for now. I will come back to what those mean. But for now and our purposes, I just want to go down to this last box labeled coefficients, because this box gives us the coefficients needed to complete our regression equation. So you can see here, I'm going to look at this part that says unstandardized coefficients. The column is labeled with a capital B. This first row, this value, that corresponds on the row of constant under the column B, so 94.326. This is going to represent the intercept of our regression equation, or as we've called it, letter A. The line right below that, associated with absences, negative 5.390, is going to be our slope, or in our regression equation, our B. So your book does talk about how you can calculate those by hand. It goes through an example. If that makes sense to you, that's great. But this is a little bit of a shortcut to use SPSS to pull that intercept and slope. So remember the 94 and the negative 5, and we're going to jump back to our slides and see how we can use these two numbers. Jumping back to our slides here, I went ahead and took those two coefficients, the slope and the intercept from SPSS, and entered them into our regression equation here. And I went ahead and plotted a line on our scatter plot. So let's think a little bit about how we can unpack a little on what this line means. So we said that Y with the little hat on it is our predicted exam grade. And we said that x is our number of absences. So now that we know the slope and the intercept, we can use this equation to kind of make guesses or predictions about what we think might happen to our exam grade based on how many days we missed class. So if I missed 0 classes or entered in 0 for the x, 0 times negative 5.39 would cancel out to 0, and I would add the intercept of 94.3. So based on this equation, if I missed 0 class periods, I would expect a 94% on my exam, which seems pretty good. You can see that if I plug in 1 for x, I would basically get negative 5.39, subtract that from the intercept of 94. So I'd be at about an 89-ish% for missing class once. So you can see that for every additional absence or every increase in x, we would expect our exam grade to drop by approximately 5 points. So you could see what would happen if I plugged in 10, 20, you'd kind of get some nonsensical numbers. But really the idea is I can use this equation to kind of model what I think might happen given information on x to predict what I think will happen on our y variable. So in this example, it's kind of a college student's dream because you could imagine what's the most I could miss class and still kind of get away with it and pass the course? What's kind of that optimal level? Where's that cutoff point? So that's what the regression equation is telling us at this point. This slide just has another example of how we could use this regression equation to make some predictions. So let's say that I knew I was going to miss 6 class periods in a semester. I could put in 6 for x in my regression equation, and you could see I could use that to solve for y. So if I missed 6 classes, multiply that by the slope, add the intercept, I would predict my exam grade to be almost a 62%. So probably not quite making it to that passing level. So our regression equation allows us to make predictions based on this regression equation and the data we have available. So a logical question might be, how accurate is that regression equation? What happens if I miss 6 class periods and I am still able to pass the course? Or what happens if I only miss 2 and I still fail for some reason? Because we know with anything in statistics, there's always that probability or chance that we're wrong. You can see here we have an illustration, and the question is, which of these figures do you think is making the stronger prediction and why? I would guess that figure A is a stronger prediction. You can see the line is pretty close to those points on the scatter plot. Whereas in figure B, there's a lot more variation in those dots. They're further away from the line. They're kind of all over the place. And we can actually quantify how good our prediction is, how accurate we are, using something called the standard error of the estimate. In order to see how accurate our regression equation is, or how good we are at making predictions with it, we'll need to look at something called the proportionate reduction in error, which is also sometimes called the coefficient of determination. And all this is doing is quantifying how much more accurate our predictions are when we use a regression equation or a regression line instead of using just the mean as a prediction tool. So you might imagine if we had no information available, let's say I didn't even keep track of absences in my class, I know nothing about my students, all I know is their exam grade. If I wanted to guess at a student's exam grade with no other information available, my best bet would be just to calculate the class average, and the average or the mean would be my best guess. So if I knew no information about you and how you might do in this class, I would just kind of guess you might get a 76% on the exam with no other information available. And you can see here I've drawn in a line at 76%, or the class average on the exam. And you can see I've drawn these vertical lines with the dots to kind of show how accurate I am. You can see that guy there with the red arrow pointing to it. It's pretty darn accurate. This person is right on the line. These are very close. But you can see for this person here, they're quite a ways below the average. Similarly, these two people are quite a ways above the average. So the mean, or guessing the average for everyone, it's not awful, but it's definitely not very accurate in looking at this graph. So the question is the regression line doing a better job of fitting these data than just guessing the mean for every single person? So we could calculate this idea of error when we predict the mean for everyone. So again, if we do not have a regression equation, our best piece of information is to just predict the mean for everyone's exam score. So we know we'll have some error because not everyone is going to score exactly at a 76%. So what this table is doing is it's taking every single student, their actual grade, or Y, and we're seeing what would happen instead if we predicted 76 across the board, the mean. And all this is doing is it's taking their actual grade, subtracting their predicted grade. You can see here 82 minus 76, I'm off by 6 points, and then squaring that error. And then at the very bottom, I would sum all of these squared errors up, and I would get something that we call our sums of squared total, which is kind of similar to what we calculated when we were talking about ANOVA. So you can see here I've done this for every single person. I take their actual grade, I subtract my best guess of the mean for every single person, subtract that difference, square it, sum it all up, I get a sum of squares total of 2,262. So the question is, can I get this number down? Can I reduce some of the error by using the regression equation instead of just the mean for everyone? And that's exactly what this slide is doing. So here I'm taking my regression equation, again, that we generated a couple slides back using SPSS, and I'm plugging in their number of absences, and in this case, someone who is absent 4 times, I would predict them to score about a 72 on the exam. So that's this column with their predicted Y hat. Now in this case, I have their actual grade data. So I know this person missed 4 times. They got an 82. I would have predicted they got a 72. And again, I can subtract their actual grade from their predicted grade and get this error. And I can then square it. So you can see for this person, I was off by a couple points here. You can see this person at the bottom, they missed 3 times. Their prediction was very close to what they actually received. But the idea is, if I take all of these squared errors and again sum them up, in this case we have sum of squares errors, and you can see I'm at 623.425 compared to the previous slide of over 2,000, we can see that I've cut that error down quite a bit. So by using the regression line to predict, instead of just guessing the mean of 76% for everyone, I've reduced my error quite a ways. And you can see here kind of 2 examples. So again, we had guessing the mean for everyone on the left. We had the total sums of squares that we calculated. On the right, we have that regression equation, and you can see how it kind of fits the data better. It's hitting more of those points. The points are a little closer to the line. It still isn't perfect because we know that nothing in statistics or research is, but it's a much better fitting line compared to that original one on the left-hand side. Jumping back to our SPSS output, I said I would revisit this and kind of explain what the rest of these boxes mean. And hopefully at this point, these numbers will look a little familiar. So this table labeled ANOVA, you can see here, it's a source table, just like with our analysis of variance unit. And really, it's kind of the same underlying principles when we're talking about regression. So you can see here our total sums of squares, 2,262. That should look fairly familiar. That was that sum of squares for just predicting the mean for everyone. Our sum of squared error, or here it's called sum of squares residual, your book uses both terms. We can see that that is 623. Again, that should look familiar. And this top one, if we take the total sum of squares, subtract the residual, it will give us sum of squares due to regression. So basically, we'll take these sums of squares and calculate a mean square and ultimately calculate an F ratio, just like we did for ANOVA. And the idea is that this F ratio is telling us how much better we're able to predict using that regression equation relative to just guessing the mean for every single person. So again, it's a ratio, just like our ANOVA, but in this case, it's telling us how much we've improved our prediction ability. And in this case, we have an F ratio of 21.027, and SPSS is telling us that that is significant. So we're doing a significantly better job of predicting using our regression equation than just guessing the mean for every single person. The other piece of output I wanted to point out is this model summary table. So I started out talking about that idea of taking your correlation coefficient and squaring it and turning it into a percent to explain a proportion of variance, or what percent of the pie are we able to explain. So again, these numbers should look familiar as well. We have our R, that 0.85, that was our correlation coefficient. We have R squared, that 0.72. And again, if we just move the decimal 2 places to the right, I would get an R square value of about 72.4%. So what that's telling us is that about 72.4% of the variation in exam grade, in this case, can be explained by absences. And the ANOVA table is telling us that we're doing a significantly good job of predicting that variance. So you might imagine, if we're able to explain 72%, how do we explain 100% of what's going on in the student's exam scores? Or how do we get as close to that as possible? So you might be thinking to yourself, we know that exam score is probably influenced by a number of factors. So clearly attendance is a big deal. But you can also imagine it's impacted by other variables. So maybe a student's motivation, maybe their general intelligence, maybe how many hours they spend studying, maybe their support systems that they have at home. So there's lots of other variables or factors that might be at play here. So this is when we move beyond simple regression of one IV, one DV, and we can move into multiple regression. Going back to the slides, multiple regression is a technique where we're including 2 or more predictor variables, or IVs, independent variables, in a prediction equation. So the simple linear regression isn't giving us a whole lot more information than just that correlation coefficient. The nice thing was we have that equation and we can kind of make predictions or guesses. We can plug in different numbers for X and see how our predicted outcome on Y turns out. But really, it's not giving us a whole lot more. Whereas multiple regression is very powerful. It can provide a pretty impressive array of information. So continuing on with this example, let's say that I think that exam grade is affected by class attendance, but also by SAT, which we'll say is kind of a proxy for students' general intelligence. So we could add the second independent variable or predictor and get a new regression equation. The only thing that has changed, the y hat or predicted score on exam grade, is the same. We still have A, we have an intercept, except now we have x1 is absences, x2 is SAT, and we'll have a slope for each of these equations. So you can see it's kind of like pulling different levers to see how our final outcome of exam grade might change. So by including more than one independent variable or more than one predictor, this new regression equation allows us to do a couple more things. We can see whether the 2 variables combined or are significantly related to or do a good job of predicting our outcome. And we can also look at how much of that variance is explained by those two variables together. So again, trying to move that 72% to a higher number. It also tests whether each of the predictors is significantly related to the DV while controlling for the other one. So we can look at their individual contribution, or we can look at their contribution as a pair or a set. We can also see which of the two predictors is a better predictor, and we'll look at how we can use SPSS to determine that. So one thing to consider, because you might be saying to yourself, well, how many independent variables or predictors can I use? Can I just put a whole bunch of stuff in and see what's the most powerful one? And this is where it gets a little bit tricky, and where kind of our logic in looking at prior research and prior evidence comes into play. So in multiple regression, we're trying to use multiple predictors to explain variance in the dependent variable. So we want our predictors, or our IVs, to both be related to the dependent. But we don't want our IVs or predictors to be too closely related to each other. So we want our predictor variables to explain a unique or an independent portion of the variance in the dependent variable. So we want our predictors to be related to the DV. We don't want our predictors to be too strongly related to each other. When we have strong correlations among our predictors, we run into an issue called multicollinearity, and this can give us problems in multiple regression. It can make it difficult to determine what the unique relationship is between each predictor and the dependent variable. So you can see here on this Venn diagram, I'm trying to explain exam grade, the pink circle over here. I want absences and SAT to both be related to this pink circle, but I want to minimize the amount of overlap between absences and SAT. I want to explain a unique proportion of exam grade and not too much overlap here. Let's jump back to SPSS for a minute. You can see here I've added a third column of SAT as a new variable. And I want to look at how this is going to impact both our regression, but first let's take a step back and see how it might influence our correlation coefficient. So if you recall, we ran the correlation coefficient under Analyze, Correlate, and Bivariate. I'm going to move all three variables over and just hit OK. And you can see here it's given me a slightly larger correlation table or correlation matrix. The correlation between absences and absences is still 1. The correlation between absences and grade is still negative 0.851. And here we can see that absences and SAT, so our two predictors or IVs, they're correlated at negative 0.58. And you can see here the significance is 0.079, not quite reaching that threshold of 0.05. But if we go down and look at the grade row, we see that grade is correlated with absences. Again, that's redundant info. Grade is correlated with itself, and grade is also correlated with SAT at 0.864. And again, that's less than 0.05 on the significance. So this is a good example of how we want both of these IVs, we want absences and SAT to both be related to grade, which they are, but we don't want them to be too correlated with each other. And you can see here they're not quite reaching a significance correlation with one another. Next, let's look at how we can run a regression equation using two predictors instead of just one. So again, I'm in the Analyze menu, Regression, and Linear. And the only thing I need to change here, the dependent variable is not changed, it's still exam grade. I still have absences as a predictor. I'm just going to transport SAT and add it to that block of independent variables. And then we can go ahead and hit OK. So here we have very similar output to our simple linear regression. You can see here I've entered two predictors. My dependent variable has not changed. One thing to look at though is look at this model summary table. So our original little r or Pearson correlation was at 0.85 and we can see now it's gone up to 0.965. Similarly, if we square that value for our R squared, or our coefficient of determination, we've gone from explaining about 70-ish% of the variance in grade to explaining 93%. So we've bumped up that R square value quite a bit compared to just using one variable. So in theory, we're making a better prediction by including the second predictor. You can see here on the ANOVA table, again, that F value is even larger this time. The significance value is very small. It's showing up here as 0.000, but it's actually just a really small decimal place. So again, this is saying that overall, we're doing a significantly better job predicting exam grade by using those two independent variables than just simply guessing the mean for every single case across the board. So the really interesting table, though, that we want to pay attention to again is this coefficients box, the very last one here. So here we still have our unstandardized coefficients. We have this column B. We have our intercept that corresponds to the row labeled constant. We have a slope associated with absences, and now we have a slope associated with SAT. So we could take those values and plug them into that newly generated regression equation we had before. So again, if we had 0 absences, and for some reason someone scored a 0 on the SAT, we would predict an exam grade of about 33%. So that doesn't make a ton of sense because the likelihood of that happening seems low, but you can imagine you can plug in different values for either absences or SAT and see how your exam prediction fluctuates. So these unstandardized coefficients, this B column, these numbers are in the original metric in which the variables are measured. So exam grade is going to be on that 0 to 100 scale. Absences is measured in days. SAT is measured in points. So this is useful in the regression equation because we can kind of see how our prediction or our exam grade might change. But in terms of figuring out which one's doing a better job of predicting compared to the other one, we'll want to move over to this column called standardized coefficients, or beta. So betas are standardized, which means we can compare them to each other. And they're kind of similar to our correlation coefficient because it'll tend to be that bounded value. It can be either positive or negative. And the larger the beta value, the stronger it is as being a predictor. So you can see here, these are fairly close. We have 0.527 versus 0.558. You can see that the SAT beta is slightly larger than the absence beta. So it's maybe doing a slightly better job of predicting than absences, but if we carry this over to the significance column, we're seeing that they're both actually doing a significant job of predicting exam grade. It's just the SAT is a tiny bit stronger. So you could imagine a scenario where, let's say SAT wasn't a very large beta, and let's say it wasn't statistically significant. That would tell us that SAT is not doing a really good job of predicting, and we might not want to measure it. We might not want to include it in our regression equation. We might be better off with just using absences by itself. So that's a little bit of a breakdown on how we can read our regression output and how the multiple regression output differs from the simple regression. Jumping back to the slides, this is just a summary of what I just talked about in terms of the SPSS output, looking at the unstandardized versus standardized. There's probably a little bit of an argument in terms of researchers and scientists which one you report in a journal article. I've seen people report both. Some people really like reporting the beta weights because you can compare them. Some people really like reporting the unstandardized because it's measured in the original metric. So I always tell you to ask your advisor or kind of read in journal articles what seems to be the convention in your field. That can be helpful to guide you. There's, again, a handout, an example posted that walks you through kind of an example of when multicollinearity might be a problem. Because really, we can use regression in a lot of ways. We can use a lot of variables to input to see if we can improve our prediction. But we want to do so with some intentionality. We don't just want to go on a fishing expedition and throw a bunch of variables in and see what comes out significant. That's what some people actually do for jobs, people who are in data mining and kind of big data analytics. But in terms of using regression for research and to answer research questions and test hypotheses, we really want to be smart about what we put in the equation, and we want to make sure that it kind of makes logical sense and it's built on a good foundation of theory and prior empirical evidence. So that is our simple linear regression and multiple regression. Again, the bees versus beta weights, looking at the output. I would encourage you to take a look at the handout that's posted. It has another example. So that is our correlation and regression. Hopefully it's been interesting, maybe a little bit easier conceptually to wrap your brain around than some of the ANOVA and factorial ANOVA. And we'll continue on next time talking about yet another branch of statistics. We'll look at some non-parametric statistics for the next week.